Hello everyone, this is Dr. Naveen Kumar from Christ University, Bangalore, India, and I'll be presenting our paper titled Deep Learning Analysis of Satellite Images for UN SDG Monitoring in Mauritius Black River District. This is an outcome of our joint research project that we did with our colleagues in University of Mauritius and at Christ University as well. Now, a little brief about the context of Mauritian, as an island, Mauritian as a country. Most of us already know that it's a small island nation in Indian Ocean, and interestingly, it has gone a significant development in the last couple of decades. And most of the focus still, of course, remains in agriculture, but there are many other sectors which also have come up in the last couple of decades. And this is quite important for rural population. Of course, it's supported by government initiatives or climate resilient practices. Now, the urban settlements are mostly concentrated in the coastal areas and the central plateau of the island, and it even has one of the Africa's highest literacy rates because of the compulsory free education for all. Mauritius has diversified a lot in the recent years into energy sources with the investments in solar energy, wind energy, and of course the energy generated from bagasse, sugarcane bagasse, right? Although being an island state, it is vulnerable to climate change, which leads into adapting various flood management as well as coastal protection plans and techniques. Even after all of this, Mauritius has achieved notably in most of these 17 UN SDGs, and this is what our project and this research focuses on. How do we monitor? How do we analyze what UN SDGs are better performing in a country or needs a special attention, right? So the research problem that we came up with, for which we did the research and presenting some of the results over here for one of the district. So the challenges in the Black River district, what we observe is that it faces a lot in terms of urbanization, demand for agricultural land for higher production, the forest conservation becomes a critical issue, and also the degradation in land because of the overusage or various other activities in the area. So these challenges directly relates to few of the UN SDGs which we shortlisted, which we selected, which fits well. And you can see over here there are three UN SDGs that we can connect with. One is no poverty, which is linking the settlement monitoring or poverty reduction in that area. SDG 2 leads to zero hunger, and of course it connects with the food security, and that further connects to the green farm and farmland analysis or agricultural land analysis. And SDG 13 goes in the domain of climate action, which involves tracking forest cover or reduction in forest coverage, and also the bare land arrangement in that particular area for climate resilience. So the objective that we come up with for this research is to develop an integrated strategy using Earth observation data and also the deep learning analysis to classify land cover and to monitor progress towards these selected UN SDGs. So the methodology that we used is pictorially, visually given on the left side of the screen, and on the right a little brief about what all these different levels and stages include. So it starts with the satellite image collection, which is nothing but getting an optical image, RGB image of that area. So we got that procured or bought from one vendor which provides satellite images. And then the next step is to go through data acquisition, pre-processing, and of course developing a CNN model to train it, test it, and finally evaluate it on the images of the Black River district. So the model basically contains CNN layers, 3 layers of different filter numbers, and max pooling layer for dimensionality reduction. Flattening is provided by a dense layer of almost 128 neurons. In the end, towards the end, dropout layer is to regularize to prevent any sort of overfitting, and the final softmax layer is to provide a multi-class classification. Now the training parameters which were chosen were using loss function of categorical cross entropy, optimizer named Adam. The metric we focused was on accuracy, and the epochs that we found good level of accuracy and very low loss is around 40. So the data acquisition, as I told you, was done by a satellite constellation named SatLogic, and the provider was Sky-Fi, and we covered most of the district, Black River district, almost 137 square kilometers, and this resolution was around 50 centimeter. The training data set was taken from RSICB benchmark, which contains almost 24,000 satellite images across 35 different categories. Out of those categories, we chose 4, which fits with our goal, which is green farmland, agricultural land, right, and bare land, forest, as well as city buildings. And these images were further split into 80% training data set and 20% validation set, where the training data set totally contains 1196 images. And during the training, over the different 40 epochs, the data was augmented by flipping, zooming, or rotating to dynamically generate almost 47,000 plus images to get a better training, right? And the satellite images that you see on the right that we bought was further divided into smaller images of 256 by 256 pixels so that they could be classified later by the trained model, which resulted into almost 1495 images after removing the images with clouds or cloud shadows, right? And these are some of the example images of the training data set, right? Covering 4 major categories. So of course, as I mentioned, there were almost 1196 images of such different categories. Now the model performance could be seen by the training accuracy and also with the training loss, along with the validation accuracy and validation loss. So we can see in both the plots that above almost 32 epochs, the accuracy peaks or accuracy achieves the highest value, and the loss reduces to the minimal, right? So that confirms that the model is not showing any overfitting or underfitting signs, and the model will work well with the evaluation of the images. Further, it is justified by the classification report as well as the confusion metrics, which tells us for each of the category what accuracy the model has achieved. Overall, it was 98%, and the confusion matrix also shows us diagonally one right unity sort of diagonal values, where it confirms that there is no kind of misclassification or there is no confusion coming from the model. So this lets us try this model to classify the images for the satellite image we have, and the application of such monitoring would be to, of course, identify urbanization or informal settlements in the area to tell us, okay, there has been some poverty elevation, and for the SDG 2, it is to monitor the agricultural land, availability of cropland, and to the changes that it brings for the food security analysis. And monitoring the forest and bare land would be tracking the climate impact on the land use, and of course the degradation, if at all, is there. So this model we basically ran on the images that we have from the satellite images. We converted from the bigger image of Black River region, and we got to see a classified output in this term, where you can see at the top of each image there is a confidence score, where 1 means the model is fully confident that it is of that category. So you can see for city building is 1, forest as well as green farmland is 1. For bare land it's 99%, so it means 99% confident that it's a bare land. So in this way, a few of the images, classified images, are shown over here out of those 1495 images that we have from the model. So we classified all the images, and we observed that the model works well around all those 1400 plus images, right? So the conclusion comes as this work successfully demonstrated that a deep learning model could be developed to analyze satellite imagery, and of course for UN SDG monitoring, how can we apply that? The proposed model achieved higher precision up to 19% and 98% of overall accuracy, classifying the key land cover types. And this approach could be scalable, of course, and it could be used to have much accurate tool for Earth observation applications, not just for these categories, it could be extended for other categories as well. And later on, we plan to do in future comparison with the other established bigger dataset models like ResNet, EfficientNet, or Vision Transformers. We could compare the performance with our proposed model, and also to assess the trade-off in terms of computational complexity, efficiency, the time it takes to classify, right? And further, we plan to expand the classification into much more number of categories, not just 4, to cover more number of SDG indicators out of those 17, and also to identify much more in terms of land cover, right? So I would like to acknowledge over here the fund that we received from University of Mauritius for this project, and also the in-kind contribution that we had from the Christ University to support this project. So thank you all for your time.